So I'm having an issue trying to find the paths for finding the nominal area. Does anyone have any idea how to properly do it?
Yeah, I don't get it either. There's just so many squigglies that can be drawn through the bolt holes.
So I understand how to do the yielding since there are two members. We need to check both of them. Check the LRFD, recalling that phi tension yielding is equal to 0.90 and Fy is equal to 50 KSI for an ASTM A572 grade 50 steel. We just need to figure out which member has the lower gross area. If we do a quick calculation, it shows that the PL38 by 10 member would control, leading to a VPN of 168.75 kips.
Let me steal your pretzel real quick.
I guess you can have one.
Sweet. Okay, so I saw this trick on the interwebs. You take the pretzel and the holes represent the bolt holes, while the webbing is the steel material. Now remember, this is only to show what happens to the material.
Whoa!
So this is a possible fracture path. Now we need to calculate which one controls. Basically, we have to compute all of them and use the one with the lowest value.
Very interesting. Do you mind handing me a piece so that I can give it a try?
Yeah, I guess everyone can have a pretzel but me.
Hey, I see y'all got some pretzels in here. Can I have some?
No!
Okay, so if I break it here, that'll be equivalent to a potential fracture path. So a potential path would be like this.
That's what I got. Looking at the PL38 by 10 member, I would expect it to fracture at the forward edge of the connection or the left bolt line, which is the green line on the picture. For the PL1/2 by 8 member, we would have a fracture path matching the blue squiggly line sketched. When doing the fracture calculations with LRFD, keeping in mind that phi is equal to 0.75 for the fracture limit states and F sub u is equal to 65 KSI for the material, all we have left is to calculate the effective area. For plate connections, shear lag factor U is equal to 1, so the effective area depends on the net area, for which we had an equation in the last episode. Wink wink. Since I take such steeltacular notes, I've got that equation right here. Both fracture paths cross through two bolt holes, so the end of the equation equals 2. We can plug in the hole diameter from AISC table J3.3. Our calculations show the net areas for both members happen to be the same, so either one could be the critical path. In calculating the design strength, we get 146.25 kips. For the final step, we compare VPN for both the yielding and fracture. In this case, the fracture will control. But for a staggered bolt layout, don't we have to consider more squiggly paths?
Exactly. Now there are a few more paths that the fracture can follow. If you can see, there are some options that are plausible, but not likely due to the load being distributed through the bolts in front of the path.
That makes sense. I'm sure there's an equation that describes that, right?
You know it. I remember reading about fracture in AISC Chapter D and how A sub n is defined in a few paragraphs in Chapter B 4.3b. We can represent the equation as A sub n is equal to A sub g minus n times dh plus a 16th of an inch times t plus the summation of s squared divided by 4g also times t, where dh is the nominal hole diameter given in table J 3.3 and the summation is the number of diagonal paths traveled between the bolt holes. This little extra area along the diagonal or hypotenuse helps to increase the strength of the member by failing in that particular path, but might control if the path intersects more bolt holes than the straight path.
Okay, let's see. Let's work out this one problem and compare answers. How does that sound?
We're game.
Same.
Alright, I'm finished.
How in the world? I'm still trying to find the paths.
For this particular problem, there are only a few paths that are realistic. You might be overthinking this.
You're probably right. Let me look at this again.
I think the yielding and the straight fracture paths remain the same, but now we have to consider a fracture line along a stagger path. For the PL 3/8 by 10 member, we probably want to consider the path 3 shown in orange, and for the PL 1/2 by 8, it could possibly fall in the fracture path 4 shown in pink. Now, all we need to do is use that nifty formula that accounts for the stagger to calculate the net section area. For the stagger, we add the sum of the S squared divided by 4G times the thickness T for every diagonal that the path goes through. For N, I am going to use 3 because that is the number of bolt holes the fracture path goes through. For this problem, the stagger, or the longitudinal spacing S, is equal to 1.5 inches, and the gauge spacing G is equal to 2 inches. We see that path 3 along 2 diagonals, so we will need to multiply the S squared divided by 4G times T by 2. The same applies for path 4. In completing the calculations, we see the critical fracture path was the staggered path through the PL 1/2 by 8 member. We use this to calculate the effective area and determine the design strength Phi is equal to 135.53 kips. Since this is lower than the yielding strength, it controls the design of this connection.
So what did you two get? I got A.
Same.